Welcome back. We're doing section 3, which is called the Aldol reaction. And we'll work through the Aldol reactions, and then I'll have an additional video that talks about crossed Aldol reactions. This section of chapter 22 is very large, and so this is where most of the meat and potatoes comes in. The Aldol reaction is an important carbon-carbon bond-forming reaction that starts with aldehydes. And what you form from the chemical reaction are aldehydes that have an alcohol functional group. So it's an aldehyde alcohol. We abbreviate that aldol. Okay, so here's a typical reaction. We have acetaldehyde, and this can react with sodium hydroxide in a protic solvent, all right, to give you the aldol product. Now, at first glance, this looks kind of weird. Where do all these carbons come from? If we were to balance this chemical equation, we could see that we need to have two equivalents of the acetaldehyde, and we form one equivalent of the aldol product, okay? So these two molecules come together, and there's a new carbon-carbon bond. It's a beta hydroxyaldehyde, okay? There's a hydroxyl group at the beta carbon with respect to the aldehyde. So this is a beta hydroxyaldehyde, okay? If we wanted to name this, we could number the carbons, okay? And we would have a hydroxyl group at carbon 3. 3 hydroxy. Okay, and 3 carbons, well, I miscounted, didn't I? 4 carbons is butanal, okay? So it's 3 hydroxy butanal. Okay, so you've got the al, or the alcohol, and you've got the aldehyde, so it's an aldol, okay? It's an aldol product. Let's look at a couple of other chemical reactions. Again, keep in mind that these reactions are in equilibrium, okay? So let's look at the reaction between butanal and sodium hydroxide and water. So if I might, I will highlight where the 4 carbons are coming from. This is an aldehyde starting material, okay? There are your 4 carbons, and here is your aldehyde starting material, and you can see how there's a new carbon-carbon bond right there. At equilibrium, you have about 75% of the product and 25% of the starting materials. And that's just an equilibrium mixture that exists when this reaches chemical equilibrium. If we look at cyclohexanone, the cyclohexanone is not an aldehyde, but ketones undergo the aldol condensation as well. And this guy here, when you react it with sodium hydroxide and water, you form a carbon-carbon bond formation. Okay, and it's still a beta hydroxy ketone, not an aldehyde in this case. At thermal equilibrium, you have about 80% of this and 20% of this. Why is that? Well, you might think that ketones are less reactive than aldehydes, which is what we discussed. Also, this product is rather sterically hindered because of the large groups attached at the alpha and beta carbon, okay? Those are tertiary carbons, so you could expect there to be some steric strain that causes this molecule to do a retro aldol reaction and go from right to left. Okay, So that's the basics of the Aldol reaction. Let's now look at the mechanism. So the Aldol reaction involves three fundamental steps. Okay, let's take a look at acetaldehyde. Okay, and what you'll want to do is react this with sodium hydroxide by pulling off the alpha hydrogen, okay, which we have talked about previously. Okay, and this will make the enolate. Okay, the enolate. Okay, so here's your enolate. Okay, we discussed the acidity of the different components here and so on. And this is a nucleophile because it's negatively charged. It's a carbon-centered nucleophile. Okay, and if we line up another molecule of acetaldehyde next to it, you can see that acetaldehyde itself is an electrophile because of the electron deficient nature of the carbonyl. Okay, there's a delta plus on this carbon of the carbonyl. Okay, and so what happens is the nucleophile is going to attack the electrophile. Okay, so this is an electrophile, and remember that the C double bond O is susceptible to nucleophilic attack. So let's go ahead and draw the arrows in here for this step. The negative charge on this carbon, okay, attacks the carbonyl, and the electrons swoop up to the oxygen. Okay, let's label these steps. In the first step, we have deprotonation. In the second step, we have attack. And what you get from this reaction is a carbon-carbon bond-forming reaction between that yellow dotted alpha carbon of the aldehyde and now the carbonyl carbon of the acetaldehyde. Okay, and I'll dot it here and I'll dot it here, and we'll keep everything color-coded so you can see which carbon is attacking which carbon and which actual bond you make. Okay, so the alpha-beta bond is the bond that you are making here. Okay, you're making that new bond. We're going to have an OH group here, okay, and you'll have a methyl group, all right, and you'll have a hydrogen on that carbon as well, but I'm not going to, well, sure, I'll draw it, okay. And this is going to be the negative charge here because that's what you form when the electrons get pushed up to the oxygen. And then what you have is water present, which serves as a protic source to return the proton to the alkoxide, and that gives you, through a protonation step, the final molecule. Okay, so that's DAP for the sequence of events for your basic Aldol reaction. You have deprotonation, and it attacks itself, and then you have protonation at the end, okay? And the product here is an it's a beta hydroxyaldehyde, okay? So that's the mechanism there that we want to do. In problem 2215, they ask us just to practice this. So let's go ahead and do that practice problem. So in problem 15, we just need to predict the major product. We're treating these aldehydes with aqueous sodium hydroxide. So there's NaOH, and then there's water present, okay? Your textbook proposes a way to easily figure out how things get attached. And they suggest to draw two aldehyde molecules side by side like this. Okay. So here's the alpha carbon. Okay. And then we want to draw another aldehyde nearby. And I think we're able to flip this around in our mind without too much difficulty here. Okay, count your carbons, make sure you have the correct number of carbons, and that's going to form a bond to the other aldehyde carbonyl carbon, okay? So that's going to form this aldehyde and this alcohol. Okay, and if it helps you dot the carbons so you can see what bond is being formed, go ahead and sketch that in there, okay? It's not obvious for a beginning student to, just see this really easily, okay? So that would be the product there, okay, that you can draw. And the other problems are just the same. I'm not going to repeat this. Instead of this R group, you have this R group, or that R group, or that R group. It's just different, okay? Let's talk about the aldol condensation, okay? When this is carried out with heat. Let me show you what that looks like. Okay, so here's the overall sequence of events. We've talked about how when you have sodium hydroxide in an aqueous solvent like water, you will form the aldol. Now, if you perform this reaction with heat, specifically refluxing it, boiling it, something like that, you will drive off water and the alcohol will dehydrate. Recall that you can form alkenes from alcohols upon heat and acid catalysis. So here we're doing it with base, okay? Normally we just draw the reaction as one type of transformation, okay? And we draw a one-way arrow here, okay? The first step is in equilibrium, but once you drive water off, that's going to be irreversible, particularly if you're doing a distillation or you have a dehydrating agent or a drying agent in there that absorbs the water and removes it from the equilibrium. So it drives the reaction to the right. So we normally write it like this: sodium hydroxide, water, and then remember the triangle means heat. And what you want to form here is this guy here, which we call an alpha beta unsaturated aldehyde, okay? Okay, so that's an alpha beta unsaturated aldehyde. Now this can also be carried out with acid. So if we wanted to, we could take something like this, and we could treat it with H3O plus, heat, okay? And under acidic conditions, you do have the aldol reaction taking place, and under acidic conditions, the alcohol will dehydrate to give you the alpha beta unsaturated aldehyde, okay? So this is a great way to make alpha beta unsaturated aldehydes, okay? Now, the book talks about how to figure this out. If you have a chemical reaction, okay, like this, and you're trying to figure out what is it going to form under sodium hydroxide, water, and heat, okay, and you're trying to figure out, okay, what are the products, how do I draw these, okay? The idea here is that you can draw two molecules side by side, okay? So there's my starting ketone, and you want to draw hydrogens on the alpha carbon, okay? And then we'll draw an ketone right below that, okay? And I'll make that in green so you can kind of see the pattern here, okay? And remember that when you have a condensation, you produce water. So we're going to pull off two hydrogens and an oxygen, okay? So that's the H2O. And then we're going to connect these two carbons right here with a double bond, okay? So this makes this product. So here's the top ketone, and that's going to be doubly bonded, okay? And we're going to draw a methyl going this way, and then a tert-butyl going that way. Now you have your opportunity to draw the E or the Z. Those are two potential products that you might think about if you want to think more deeply about this, okay? But since this is a tert-butyl group and this is a large group here, those groups are probably going to be on the opposite sides of the alkene to relieve steric strain. So this is most likely going to be the major product here, okay? Problem 20 and 21 basically go through the process of you saying what are the products, okay? So let's do a couple problems. if we can fit these on the board. Problem 20, draw the condensation product when each of the following compounds is heated in the presence of sodium hydroxide. So there's sodium hydroxide and you're adding heat. So this is where you used that procedure before, where you line up two of the aldehydes or two of the ketones, and then you're just going to make a double bond between the alpha carbon of one and the carbonyl carbon of the other. So let's go ahead and do that. Here's my starting aldehyde, and I'm going to dot the alpha carbon there. And then I'm going to take my other aldehyde and flip it around. Okay. I flip it around because I know the big groups are going to be opposite sides of the alkene to relieve steric strain. And I believe that's the right number of carbons. And so recall again what we do. We're going to draw in two hydrogens here. And we have this oxygen here. So we're going to pull off these elements from the two molecules and then create a double bond between this carbon and this carbon. So that's going to give us I'll draw the H there just to draw it. Okay, so that's going to give us this alpha beta unsaturated aldehyde. Okay, so that's the procedure for how you do that. Let's maybe do F here. All right, so F, we want to draw two molecules, side by side so that we could see how they react. Okay, so this molecule, I'm going to draw the two hydrogens on the alpha carbon. And my other molecule, I'm going to flip it around so that the oxygen is positioned in the right direction. Okay. And so again, what I'm going to do is pull off the oxygen and the two hydrogens. And then I'm going to take this carbon and doubly bond them. So that will be this product here. So on the left, we have the ketone present. Okay. And then here's one of the carbons. That's going to be doubly bonded to the other carbon, and there's a 6-membered ring there. Okay, and then on the opposite side of the ring, I have those two methyl groups. So you want to make sure your two methyl groups are on the opposite side. That dotted line is just orientating your eyesight so you can see what the opposite side of the ring is. It's not part of it's not a bond, it's not a hydrogen bond or something. Okay, so that's basically how you do that. Let's do problem 21 to think about retrosynthesis. In problem 21, we're asked to identify the starting aldehyde or ketone that could be used in a condensation reaction to produce these various molecules. We of course know the reagents are sodium hydroxide, water, and heat. Okay, so what you first want to do is think about this in terms of the reaction mechanism and think backwards through the steps. Okay. So step 1 would be to identify the alpha carbon and the beta carbon, okay? And what you want to do is redraw the molecule with a single bond between the alpha carbon and the beta carbon. Okay? And you want to place an OH group on the beta carbon. Okay, so here's an OH. Okay? And then you want to think and fragment this molecule to think about how it could break apart, okay? So this is the bond that you're going to break apart. Okay, this guy between these two carbons, I'll use a different color here. So this carbon and this carbon get broken in that mechanistic step, and that's going to give you your two fragments, okay? So it's going to give you an aldehyde that looks like this, and it's going to give you an aldehyde that looks like this. Now, if those two aldehydes are the same, you only need to draw one of them, okay? So the reaction would look like this. Okay, we're going to take the aldehyde, treat it with sodium hydroxide, water, heat, okay, and get the target molecule. Okay, this I am defining as the target molecule. Okay, so that's how you think through it. Step 1, identify the alpha and beta carbons. Step 2, draw your molecule with a single bond between the alpha and beta carbons. And then step 3, add a beta hydroxy group to the beta carbon. And then step 4 is to think backwards through the retro-aldol reaction or the mechanism to kick off and break apart your two aldehyde fragments. Of course, the very last step is to analyze. Do you have just one structure or do you have two structures? Okay? Sometimes you can have two different aldehydes. Sometimes you have just one, the same molecule written twice, as in this case, okay? So that's how you do this problem. The textbook says to try problem 71 and 84C if you would like more practice. I, of course, would do those ones, okay? But we don't have time to do all the practice problems in this lecture video. All right? So let me just clarify a little bit. Maybe a textbook figure would be best here at this point. Okay, so this slide just summarizes what we've talked about. If you have an aldehyde or a ketone and you subject it to sodium hydroxide and water, you can do an aldol addition to give you the beta hydroxy aldehyde or the aldol product, okay? If you treat this with sodium hydroxide in water and heat, that will allow your aldehydes to give you at the end of the day, at the end of the reaction, the alpha beta unsaturated aldehyde, okay? So just kind of be familiar with some of those things. We know from biology or just English about condensation. Condensation means, you know, it's raining outside, or the windows in your bathroom might be fogging up if your fan is not operating correctly. That's condensation, right? When water forms. So if you form water, we call that a condensation reaction in organic chemistry. And the addition reaction just means those two molecules add together, and that's the final product. Okay? Let me take you through the reaction for the aldol condensation. Okay? As before, the first three steps are going to be the same as I discussed. You're going to have hydroxide come in and deprotonate the alpha hydrogen, and this is going to give you the enolate. The enolate, since it's a nucleophile, is going to attack another equivalent of aldehyde that's in the reaction mixture. And this will give us almost the addition product, okay? So this is deprotonation. This is attack or add if you want. And we're getting very close to the final product now. Okay, we get the almost the aldol product. And these electrons right on the oxygen are going to become protonated because we're operating in a protic solvent, water maybe, or ethanol or methanol or something. So this is going to be your protonation step to give you the aldol product, okay? So this should all be review at this point. We've talked about this earlier in the lecture. Now to actually remove water, what we do is we deprotonate the alpha hydrogen once again, okay? There's a hydrogen there. So we're going to take hydroxide, okay? And that's going to deprotonate, and we're going to get a enolate once again. The enolate then eliminates the hydroxide at this point. So hydroxide is going to be the leaving group, and this is going to come down, and it's going to kick off, okay? So this is yet another example in organic chemistry where you do indeed have hydroxide as a leaving group because you have an internal nucleophile, okay? We saw that with some other reactions with carboxylic acid derivatives, okay? So this is going to give you, and this step is essentially irreversible, but I'll just draw it as an equilibrium here. And so what you form is the alpha beta unsaturated aldehyde. Okay. So those are the, okay, so that's the elimination step. So let's number these out. That's DAP-D, okay? DAP-D, okay? So first step, you have deprotonation, then attack, then protonation. That gets you the aldol. And then the kickoff hydroxide, it's a two-step procedure. You have to deprotonate to make the enolate, and then the enolate fragments, and you eliminate hydroxide, okay? So DAP, DE for those 5 fundamental mechanistic steps, all right? Normally you make the E alkene is normally the major product. The reason why is because you have 2 groups further apart on the alkene and there's less steric hindrance, okay? So less steric strain. And so that's why I'm drawing the trans alkene here, not the cis alkene. You would form minor amounts of the cis and it probably would be detectable, okay? Now, you can cause this reaction to be driven by heat. So the textbook gives you a simple example here. If you take cyclohexanone and you add sodium hydroxide at, kind of refrigerator temperature here, you'll form the aldol product. And remember that this is in equilibrium and it heavily favors the starting materials in this reaction. So you might get, a 20% yield or something like that, all right? But if you do this reaction at 100 degrees Celsius, which is heat, that's boiling water, right? You're going to get elimination of H2O across those 2 carbons, and it's going to give you this product here, and the yield found there is typically 90%. Okay, why is it so high? Because it's irreversible. Once you blast off water, it can't come back readily to react with your alpha beta unsaturated product. It stops there. Remember, when you have more double bonds next to each other, we call that molecule conjugated. There's more resonance stabilization, so that's a more stable product, okay? So under heat, you can drive it very nicely to form alpha beta unsaturated ketones and aldehydes. If you don't use heat, you better hope your aldehyde is just one of those good ones that readily reacts and gives you a high yield of the product, okay? So that's the basics here. I'm gonna stop the video and I'll continue in this same section with the crossed aldol in just a moment, okay?